Oh, my word, it's Taco Tuesday again, May 19th. Welcome back, Kitchen Table Chemistry. And today we are going to get into covalent bonding. Again, as we go through bonding, yesterday was all about metallic bonding on Monday, and last week we looked at ionic things. So today, our third type of bonding, which are things that are covalent. And this is where we are, by the way, going to spend probably the rest of our time this year. Now, what is this covalent bonding? Covalent electrons are shared to achieve an octet. Two elements share two electrons. This is sort of the boot description of what covalent bonding is. Two elements share two electrons, and they are formed amongst nonmetals. Why share electrons, you say? Well, because all of the elements tend to have high electronegativities. So everybody pretty much wants an electron here, so no one's going to give one away. Remember, in ionic bonding, the electron was transferred. Here it is shared, co as in sharing, valent electrons. So that's our story. How to draw a covalent bond? So I'm going to draw one for you here. If we have, we're going to start with chlorine, which has 7 valence electrons like this. And of course, it would want to achieve an octet. And here we have hydrogen. Hydrogen is going to be this really strange element that does not necessarily want to have an octet. It only wants to have a duet. So it has what's called the duet rule with an electron like this. They are going to share, two elements are going to share 2 electrons, and that set of circled electrons there means they are shared. When we start drawing these, we're eventually going to replace that with a dash. And that dashed line equals a covalent bond. Now I'm going to put these electrons around here. Chlorine doesn't use all of its electrons to bond. So chlorine here has what are called non-bonding electrons. And non-bonding electrons, halogens have these things, oxygen and sulfur. These non-bonding electrons are electrons that are not involved in the bond but are still on the element. And they tend to have an effect, and we'll get into that. But this is how we draw it. We simply replace the circled electrons with a dash like that. Okay. Here's the idea. So here, in this example here, we've got a chlorine here and a chlorine here. And these overlap, just kind of looks like a Venn diagram, but those are the shared electrons. So what we have here in this covalent bond are 2 electrons shared by 2 atoms. Okay, hopefully that's sticking. Now, our bond lengths are going to be different. With ionics, they tended to be really, really short. But with these covalents, they can sometimes be longer, sometimes be shorter. And this is going to influence how things respond, how they behave, how reactive they are. Shorter bonds tend to be higher energy, longer bonds tend to be lower in energy. Now, some bonds are what we call polar bonds. Why is this interesting? Because this is going to lead to what is called polarity. As you know, oil and water don't mix. They just don't. And the reason why is because water is polar and oil is nonpolar. So whether or not something is polar is going to decide whether or not it dissolves in something else. So this is a big factor here. Now, covalent bonds share their electrons, but not always equally. And this is related to their electronegativity. So if you want to take, or if you haven't yet, take a pause and go and get your electronegativity chart out, because I'm going to be going to some of the values here. When bonding, electrons are shared, when bonding, if the electrons are shared equally, they're referred to as nonpolar bonds. So we have equal sharing, it's nonpolar. If the sharing is unequal, then they are polar. And I'm going to give you some values for this. If the sharing is extremely unequal, in other words, it's really not sharing at all, then the bond's going to be ionic. So they're not really sharing the electron, it's being yanked from one thing to another. Okay, so again, why this polarity is interesting? Because This I'm explaining to you now why oil and water don't mix, why some things dissolve in water and other things don't. It has to do with what is called polarity, whether or not the electrons are shared equally or not. Here's your electronegative values chart. Again, we're only talking about the nonmetals now, so we're going to be over like in this area, and we're going to have hydrogen. Everything pretty much has a high electronegative value. Okay, let's make some shapes here. Let's talk about water and let's talk about hydrochloric acid. Water here, we're going to put oxygen in the middle with its 6 valence electrons. And then I'm going to put a hydrogen down here with its electron. I'm going to put hydrogen over here with its electron. And then we're going to join them together because oxygen by itself only has 6 valence electrons, but when bonded to 2 hydrogens, it now has 8 valence electrons. So we have satisfied the octet. This is fantastic for both the oxygen and the hydrogen. Again, hydrogen is sort of that exception to the rule. It does not want to have an octet. It just wants to have 2 electrons. Now, is water polar? Yes. Hydrogen's electronegative value is 2.1. Oxygen's value is, I'll put it here, is 3.5. So it has a much greater draw for the electrons. So in this thing, the electrons are going to be drawn towards oxygen. And that is going to be shown here by the arrow. So the arrow gives us, I'll put it down here, the arrow. So the electrons are drawn in the direction of the arrow, in this direction. Why does it do that sometimes? So water here is very, very polar. This electronegative, hey, don't do that yet. Hey, this electronegative difference of 1.4 and 1.4, these are huge electronegative differences. That makes water very, very, very polar. Now, we have made up solutions of hydrochloric acid and water. Here we have our hydrogen. Now let's go back to red. Okay, so here we have our hydrogen. Yeah, I think I knew that was going to happen. Bonded to our chlorine. And by doing this again, and I'm going to have to get the eraser out because I kind of jumped ahead of myself. Okay, now let's go back. And we're using this yellow, I think. So by making this single bond, we've now satisfied the octet for chlorine and the duet for hydrogen. Chlorine's electronegative value is 3.0. Hydrogen's value is 2.1. So a little bit of visual math here says that chlorine has the greater attraction for the electrons. So the electrons are going to be drawn towards the chlorine. So in the pole of this thing, chlorine here is going to have a partial negative charge and hydrogen is going to have a partial positive charge. That's why I'm drawing sort of these things on the back of the arrows to make it look like a positive. So both of these things are polar, both water and hydrochloric acid are polar. Let's take a second here though and see something that is nonpolar. And I'm going to go to, let's go to this faint green color here. We're going to do CH4. That is the gas that comes out of the jets in the lab, the methane. So we're going to make it like this. Carbon, which is going to have its 4 electrons like this. A hydrogen here with its electron. A hydrogen here with its electron. Do not do that. Hydrogen here with its electron. And then one down here with its electron. And then we're going to circle these. And everyone has an octet, messy as it is. However, hydrogen's value is 2.1, all of them. And carbon's value is 2.5. So that low of a difference means that this here is even and all the bonds on this are nonpolar. Because they are nonpolar, methane, this gas, will not dissolve in water. Okay. This is hydrochloric acid. This on this side is the hydrogen, on this side is the chlorine. And you can see that even when drawn out, and boy, it would have been fun to have done this with you guys with the molecular kits, that it is nowhere near even. It's not an even looking structure because it is polar. Again, polar means uneven. Where do you find polar bears? At the end of the Earth, at the North Pole. So polar, uneven. Here's water, which as we drew before, and I'm just going to switch to a darker color and check. Here we have the hydrogen, and here we have, these are our bonds here. So it's allowing oxygen to have its octet. Here is my partial negative charge, and here are my two partial positive charges, making this thing polar. Again, water is incredibly polar. What does this mean? Electronegative differences in bond types. If this electronegative difference is from 0 to 4, it is nonpolar, much like the example I made. 0 to 0.4 is nonpolar. And have this in your notes, and I usually have you write it on the back of your periodic table, and that, but have it available. 0.5 to 1 point, and by that, nonpolar covalent, a nonpolar covalent bond. That's the second part there. If it's 0.5 to 1.9, then it is a polar covalent bond. The bond is polar, and the bond is covalent. And if it's over 2, it's completely ionic. So completely and totally ionic. Also, if it contains a metal, we always go ionic if it has a metal. So these are our values. So let's look at some examples. Nitrogen here has a value of 3.0. Hydrogen's value is 2.1. The difference between these two numbers is 0.9. And because that difference is 0.9, that means that this is covalent and this is polar because of the difference. Both of these hydrogens are 2.1. Because they're both 2.1, they're equal, so this is covalent and nonpolar. Here, before I even start checking my electronegativity chart, this has calcium in it. Calcium is a metal, ionic. Here, this one has aluminum in it. And again, what type of bond would it be? It would be ionic. I always want you to choose ionic if it has a metal in it. And here we have carbon, which is 2.5, and oxygen, which is 3.5. So the difference here is 1.0. So this is going to be covalent, and this is also going to be polar. In this polar molecule up at the top, the electrons are going to be pulled towards the nitrogen because of its greater electronegative value. Here, the electrons are going to be pulled towards the oxygen because of its greater electronegative value. And here, they're not pulled either way because it's nonpolar. In an ionic substance, they are transferred. Okay, I hope this is coming clear.